All right, today we're diving into a topic that is honestly pretty mind-bending: quantum simulation. We're talking about the incredible idea of using quantum computers to literally build a blueprint of reality, to model the universe at its most fundamental level. So let's unpack what that really means. But what does that mean for us? Well, imagine this. What if we could design a new life-saving drug not through trial and error, but by simulating exactly how it interacts with a single protein in the body? Or what if we could invent a brand new material that can superconduct electricity at room temperature? Or even take the wild guesswork out of our incredibly complex financial markets? And look, this isn't some far-off sci-fi dream. These are the real, world-changing promises of quantum simulation.
So, you might be wondering, why do we even need a whole new kind of computer for this? Well, it all comes down to how computers deal with complexity. Classical computers, even the biggest supercomputers on the planet, they just really struggle with quantum problems. Why? Because for them, the resource needs grow exponentially. That means every tiny particle you add to a simulation makes the problem unbelievably harder until they just hit a brick wall. Quantum computers, on the other hand, are built differently. Their resources scale polynomially, which is a much more manageable growth curve, and that is what lets them tackle problems that are just flat out impossible for any classical machine.
At its very heart, quantum simulation is a pretty elegant idea. You're just using a quantum system that we can control, our quantum computer, to perfectly mimic one that we can't, like the super complicated dance of electrons inside a new drug molecule. We're basically building a virtual laboratory where we can experiment on the building blocks of reality itself. Now, an idea this big didn't just appear out of thin air. Let's take a quick look at how this vision grew into a real, practical field of research. The journey from just a theory to something that actually works has been decades in the making. It all started way back in 1982 with the legendary physicist Richard Feynman. Fast forward to 2005, and researchers proved that quantum computers could, in principle, calculate molecular energies with that all-important polynomial scaling. Then, in 2014, a real game-changer came along, an algorithm called VQE, which was designed specifically for the early kind of imperfect quantum hardware we have today. And by 2020, the whole toolbox started to open up to everyone, with open-source software making this stuff way more accessible. So what is this VQE thing anyway? Well, it's a really clever team-up between two types of computers. Think of it like tuning a guitar. The quantum computer makes a best guess. That's like plucking the string. In the field, they call this guess an ansatz. Then, a classical computer listens to the result and tells the quantum computer how to tweak things to get closer to the perfect note. In our case, that perfect note is the lowest possible energy of the system we're studying. They just go back and forth working together until they zero in on the right answer.
Okay, so we've got the tools. Now let's explore the first major frontier where all this is being applied: digital chemistry. This is all about crafting and truly understanding molecules from the inside out, right inside a quantum computer. And right here, you can actually see the VQE algorithm doing its thing, simulating a simple hydrogen molecule. Take a look at the bar chart. As the optimization steps go on, the calculated energy drops and drops and drops. It's the perfect picture of that hybrid process we talked about. The algorithm is literally learning and getting closer and closer to the right answer with every single loop. It's proof that the method really works.
And the results? They're seriously powerful. Research has shown that VQE can hit what's called chemical accuracy for small molecules. It actually surpasses standard classical methods because it can capture this really tricky thing called electron correlation. The incredibly complex ways that electrons interact with and try to avoid each other. This is exactly the kind of quantum weirdness that just totally trips up classical computers. But for a quantum simulator, it's what it was built to do. Okay, moving beyond just single molecules, this same exact approach is helping us unlock the secrets of material science, where the big prize is to understand exotic materials that could pave the way for incredible future technologies. Now, a key test in materials science is solving something called the Fermi-Hubbard model. You can think of it as a basic blueprint for how electrons behave in certain solid materials. This table here shows a comparison. For a small version of the model, and what do you see? The VQE quantum simulation result is in good agreement with the exact classical answer, which we use as our gold standard. This is huge. It proves the method is accurate for these really fundamental problems. So why does that matter? Because this success shows that VQE can handle what are called strongly correlated systems. These are materials where electrons interact so powerfully that you can't predict their behavior one by one. They are an absolute nightmare for classical supercomputers, but they're also the key to unlocking things like high-temperature superconductivity. Being able to simulate them accurately is a massive step toward designing brand new materials from the ground up. Now, let's shift gears completely from materials science to Wall Street. It turns out the same principles of quantum simulation can be used to completely recalculate risk and reward in the financial world. The key advantage here is something called a quadratic speedup. Let me break that down. In finance, you often run millions of random scenarios to get a precise answer. For a classical computer, if you want your answer to be 10 times more accurate, you might have to do 100 times more work. But for a quantum computer, to get 10 times more accurate, you only need to do 10 times more work. That enormous gain in efficiency means you can get a way better answer way, way faster. And it's not just about being faster, it's also about being incredibly accurate. This chart here compares a few different methods for pricing a financial option. And look at that. The quantum simulations result almost perfectly matches the exact answer from the famous Black-Scholes model. That proves this approach has real-world reliability. Okay, this all sounds absolutely amazing, right? So where are all these quantum-designed breakthroughs? Well, this is where we need to take a deep breath and have a little reality check. The current state of quantum hardware gives us some major challenges to overcome. Welcome to the NISQ era. NISQ, it stands for Noisy Intermediate Scale Quantum, and it's the perfect description for today's quantum computers. They're powerful, for sure, but they're also kind of small and incredibly sensitive. The tiniest vibration, the slightest change in temperature, what physicists just call noise, can totally throw off their calculations. You can think of noise as the ultimate villain in our story. And this villain, noise, creates a whole cascade of hurdles. On the hardware side, we have a limited number of qubits, and their delicate quantum states can just fall apart. That's a problem called decoherence. Then, on the software side, designing the right circuits, or ansatz, is a massive challenge in itself. And the whole process of running them and getting a result is just really slow and complicated right now. So this brings us right to the core battle of this whole era. It's all about harnessing the incredible, immense theoretical power of these quantum algorithms on the imperfect, noisy hardware that we can actually build today. But here's the good news. That battle is one that researchers are actively fighting and making progress on every day. So let's wrap up by looking at the roadmap they're following to chart a course toward a true quantum future. First, let's just remind ourselves why this whole fight is worth it. This chart says it all. That towering red line shooting upwards, that represents a classical computer hitting that exponential wall we talked about. But that gentle rising blue line, that's the manageable polynomial growth of a quantum computer. That is the quantum advantage. It's what turns the impossible into the possible. So how do we get there? Well, researchers are following a pretty clear four-step path forward. Step 1, build better recipes. That means more advanced and efficient circuit designs. Step 2, fight the noise head-on with smarter ways to mitigate errors. Step 3, team up, designing new and improved hybrid algorithms. And Step 4, optimize absolutely everything to slash the number of qubits and operations you need for any given calculation. Because of all this hard work, true quantum advantage is really no longer a question of if, but when. It's on the horizon. And that leaves us with one final and really thrilling question to think about. When we can finally simulate reality's blueprint, what impossible problem should we solve first?